Okay, so again, really do think you should probably rewatch this lecture, even though that doesn't necessarily sound like something you might have time for. You should, I think, give it your best shot. Really listen to things I say, as well as check calculations that I say you should check, even though I'm not taking the time to do it, like this one. Okay. All right, let's come back to this example. Splitting field for, this is really two examples, x to the fourth plus 1, over two different fields, over q and over r. In both situations, we still have these same fourth roots. These are the fourth roots of -1. This one is cos 45 degrees plus I sine 45 degrees. 1 over root 2 plus I times 1 over root 2. And these other four roots are plus or minus those things, applying plus or minus to both the real part and the imaginary part by the symmetry of the picture. You can see that. You might hope then that the splitting field in both examples would be either Q or R adjoined, say just this thing. And that would be good enough. Those would be the answers. So in the first case, it's Q adjoined 1 over root 2 plus I times 1 over root 2. That's the splitting field for x to the fourth plus 1 over q. Over r, it's a different answer. It's r adjoined 1/2 plus I, well, 1 over root 2 plus I times 1 over root 2. These are different fields, different answers in the different situations. So again, you don't say a field is a splitting field of a polynomial without saying what the base field is. The answer depends on what the base field is. They look similar, but they're different. And not only are they different in terms of using a Q versus an R, but they also could have different dimensions as vector spaces over the appropriate subfields. That could be the case. And in fact, it is in this example. Why? Well, x to the fourth plus 1 is irreducible over q, but reducible over r. That's the key distinction. I'm not going to prove that it's irreducible over q. I will refer to an exercise, which does happen to be an odd exercise, so you could technically look in the back and look to see how to prove it. It's exercise number 15. Page 301 actually refers to both Q and R. Chapter 17, exercise number 15. Says, show that x to the fourth plus 1 is irreducible over Q, but reducible over R. Actually, let me verify for you that it's reducible over R here in class. The irreducibility over Q, you can again try to, if you want to know and you are trying to be efficient with your time, you can just look in the back of the book. I'll use Mathematica to do some calculations here. Expand will take polynomials in factored form and multiply them out. If, for example, I expand x minus 1 over root 2 plus I over root 2, capital I is the complex unit in Mathematica. You can also use double struck I, which you can make by doing escape, double I, escape. Makes sort of a fancy looking I there. That's hard to see. Right there. Probably easier just to use a capital I. So this is one of the factors when we factor it over the complex numbers that I'm going to consider. Here's another factor. Change the plus here to a minus. Consider the complex conjugate of this root, this one, put a minus sign there. Consider x minus both of those things. These would be factors of x to the fourth plus 1, evidently, over the complex numbers. But when you multiply these two, so I'm not thinking about the other two zeros, you actually get a polynomial with real coefficients, a quadratic. But that's not rational. It's not a proof that x to the fourth plus 1 is irreducible over the rationals, but it's a little hint that it might be irreducible. But it is reducible over the reals. This is a real number. If I expand out the other two, put minus signs in front of the first part, the real part here, this also gives me a polynomial with real coefficients, but not all rational. We get root 2 occurring again there. And then if I multiply those two things, change this minus sign to a plus, I get my original polynomial, x to the fourth plus 1. This shouldn't be surprising, because we saw those four roots in the complex plane are the things that I'm subtracting with these linear factors. So this shouldn't be surprising, but you can confirm that it's true, and you should try that by hand, maybe. Confirm these by hand. I hope you believe it more. But anyway, because you can factor it as the product of these two quadratics over the reals, it is reducible over the reals. And that has implications with the dimension question, related to that theorem that I showed you now 25 minutes ago now. What are the dimensions of these fields as vector spaces over the appropriate subfields? The irreducibility of x to the fourth plus 1 over the rationals is going to mean this is 4-dimensional over Q. But the reducibility of x to the fourth plus 1 over the reals, and then the fact that I got those x squareds that are actually going to be irreducible over the reals, is going to mean this one's got dimension 2 over the reals. So in a diagram, I could write a 4 there, dimension 4 as a vector space over here, and with the real one, I could write a 2, emphasizing this is 2-dimensional over that. This would have a basis of 2 numbers, 1 and this thing. This is going to have a basis of 4 things over with your coefficients from there. And they would be 1 as well as powers of this thing. First, second, and third powers, which is going to give you these 3. As well as 1. I wonder, does that one need to be included? Evidently it doesn't. Based on that theorem that I showed you. I went very quickly over the theorem, so you're going to want to look at that again. Splitting field for x to the fifth minus 1 over q. Here are the fifth roots of unity this time. Notice the minus 1 here instead of a plus 1. So these are not fifth roots of -1. They are fifth roots of +1. One of which is +1 itself. Another of which has angle 360 degrees divided by 5. Which is what, 72? Is that right? Yeah, 72-degree angle there. 144-degree angle for this one. 216 degrees to get to that one. 288 degrees to get to this one. And then up to 360 again. So those are the fifth roots. And so if you write Q, I don't have an R here, just a Q. Q adjoin these 5 roots, that would be a splitting field for this. Though you might hope you can write it in a simpler form. And it would turn out that that simpler form would be Q adjoined one of these, say this one right there. Let's call it omega, cosine of 72 degrees plus I sine 72 degrees. It's going to turn out the answer can be written as Q of omega. That's not too hard to prove. Q adjoin omega, and it will contain the other 3/5 roots of unity. But what's the dimension as a vector space over Q? The answer is not 5. This polynomial up there is reducible over Q. It's got x minus 1 as a factor because 1 is a root. In fact, you can factor it. It turns out as x minus 1 times, it turns out, x to the 4th plus x cubed plus x squared plus x plus 1. If you know about finite geometric series, that shouldn't be surprising. If you know about those things, which you technically should, but you may have forgotten. It's going to turn out this thing, this polynomial here, is irreducible over Q. That's actually a corollary in the book. Corollary to set theorem 17.4 on page 294, chapter 17. This is called a cyclotomic polynomial. In fact, it's the pth cyclotomic polynomial, where p is 5, prime 5. And the corollary on that page does say it's irreducible over Q. And it's actually a situation where Eisenstein's theorem is applicable, though you have to do a little trick first. Eisenstein to prove this is irreducible. And what this is going to mean is that because that has degree 4, the dimension is going to be 4. That theorem I showed you from the first lecture. That was in the last lecture that I didn't give. Okay? So the answer is going to be, the dimension is going to be 4 as a vector space over Q. You have a basis with 4 elements. Those elements would be 1 and omega, omega squared, and omega cubed are written. All right, with the time we have remaining, well, I was wanting to do an example like this, but we don't have enough time. We'll come back to an example, probably not enough time at least. Maybe we will. I guess we have a little bit more time than I was initially thinking here. If we have time, we'll come back to this example at the end where we're talking about the splitting field for a polynomial over a finite field. The book has plenty of examples of this. You should study them. We will come back to an example like this. If we don't have time for today, we'll come back to it on Friday. Probably we're going to just focus on some definitions and theorems here in our time remaining. Before that, some insight into our notation, and this is definitely worthwhile to know about. Given a commutative ring R, we have defined this symbol to be the ring of polynomials with indeterminate x with coefficients in R. Right, write the ring there, write x inside square brackets there. We've also seen if f is a field, if the ring is a field, then in fact this polynomial ring is a principal ideal domain and also an integral domain. Actually, it's good enough for R to be an integral domain to make the ring of polynomials an integral domain. Fields are certainly integral domains, so it's definitely true for fields. But in addition, it's a principal ideal domain, just reminding you of some facts. Notation such as these kinds of things is actually consistent with this. What's that? That's the Gaussian integers, right? I is the imaginary unit here. This notation is actually consistent with this notation. This is a ring of polynomials with coefficients in R. Is this a ring of polynomials with coefficients in Z? Is I the indeterminate? Well, yeah, it is, though I has extra meaning, is the extra fact here. When you write a polynomial out, that's a polynomial in I, where I is the imaginary unit, you can always simplify it down to the simpler form. This, by the way, is the Gaussian integers here. You write a polynomial in I like 5 plus 7i minus 2i squared plus 4i cubed plus 3i to the fourth. You can simplify it using the fact that I squared is negative 1. This becomes a negative 1. This becomes a negative I. This becomes a positive 1. So it simplifies down to our simpler form. The real part is going to be 5 minus 1 plus 1 is 5. The imaginary part, we're going to get got a 7i there and a minus 4i there, so we get a plus 3i in the end. But initially we thought of it as a higher degree polynomial in I. It can be simplified based on the fact that I squared is negative 1. Z adjoining root 2, that's a ring where we've said it looks like this. But this could also be thought of as polynomials in the indeterminate root 2. If I go back up here and replace all these i's with root 2's, like that, I can use the fact that root 2 squared is 2 to simplify that down to the simpler form. That'll be a 2, that'll be a 2 root 2, and that'll be a what? 4. And I can simplify it down to the simpler form. More notation. What if we use parentheses instead of square brackets? Where we're talking about polynomials, so to speak, in the abstract. Given a field f, it is also possible to define a field f of x. This is not a function here. Careful, it's tempting to think that's a function. To be the field of rational functions. Its elements are functions. Quotients, if you will, field of quotients. In the indeterminate x. In other words, ratios of polynomials in x. With coefficients in f. That turns out to be a field. An element of the field is, for example, 5 plus 4x minus 3x squared over 7x plus 5. Whatever. Ratio of two polynomials with coefficients, say, from the reals. Set of all such things forms a field under ordinary addition and multiplication of rational functions, of fractions. What's the multiplicative inverse of this thing? It's its reciprocal. 7x plus 5 over 5 plus 4x minus 3x squared. We're going to multiply together to give you 1, which can be thought of as 1 over 1 or 2 over 2 or whatever. Technically speaking, there are some extra complications that come in from the fact that fractions can be represented in different ways when you do this. You're really talking about equivalence classes of fractions. You know, y's, 2/3 and 4/6 are different as symbols, but they're equal as fractions. There's really an equivalence relation going on there that technically needs to be defined. I did talk about this one lecture a long time ago, maybe 2.5 months ago or something. And that needs to go on with these ratios of polynomials as well. But after you do that, you can show the field. And that's what this notation represents. Our new notation with these field extension ideas is consistent with this. Misplaced the clicker. Notation such as this is consistent. Q of I, where I is the square root of -1, could be thought of as the set of all rational functions in I. It would take proof, but it can be simplified. All such functions can be simplified to say that you can write these elements in a simpler form, a plus bi, where a and b are rational. That would take proof if you're initially assuming this is the set of all rational functions in I, ratios of polynomials in I. You'd need to prove that you can do this, but you can prove it. Shouldn't be too surprising. You can take, here's an outline of the proof, you take your arbitrary rational function in I, top and bottom are both polynomials in I, which you can simplify down to the simpler form individually on the top and the bottom. And then you can multiply the top and the bottom by the complex conjugate of the bottom to simplify to something like this. It definitely can be done. Adjoin square root of 2, you can think of it in a similar way. Adjoin pi. So this would be as a set, thinking of it this way, this would be the set of all rational functions where the top and the bottom are polynomials in pi, where pi is taken to represent the number pi, the ratio of the circumference of a circle to its diameter, that irrational number. Can such rational functions be simplified to something simple like this? The answer is no. There's something fundamentally different about pi compared to I or square root of 2 that prevents that. And that's the main subject of chapter 21. Before we get into that, we need to make a definition here. Maybe, since we have a short amount of time, don't write these down. Just think. These are in fundamental definitions and theorems at the beginning of chapter 21. Just listen and think here. Okay? E is an extension field for F. Draw a blob picture here. So here's F. Here's E. A is in E. A could be in F as well, but it's usually more interesting to imagine it's not. A is said to be algebraic over F if A is the zero of some non-zero polynomial in F of X. Polynomials with coefficients in F. Think with examples here. If A is I is a zero of x squared plus 1. I is going to be algebraic over both Q and R. For example. If A is not algebraic over F, it's said to be transcendental over F. Makes you think of transcendental meditation or something. Do you know what this song comes from? Do 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 do. Do you know where that comes from? Nobody? Nobody? Really? Do 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 do.
Is it the Twilight Zone?
Twilight Zone. Yeah, that's it. Transcendental. Twilight Zone. If you've never heard of the Twilight Zone, look it up. They're great. Okay, old TV show from 50s, I think, maybe 60s. Black and white for the most part, I think, but very interesting stories. And that's the song at the beginning of the show. Okay, an extension E is called an algebraic extension if every element is algebraic. If there's at least one element that's not algebraic, then it's called a transcendental extension. And an extension of a form where you're joining one element in E, not in F, is called a simple extension of F. And again, I guess the element could be in F. And then you're not really getting anything new when you do that. historically speaking, this is very important stuff in math. I call it a historical curiosity here, partially because it is curious. But it's actually also important. It's historically important math. It can be proved fairly easily that almost all real numbers, in quotes, are transcendental, actually. The algebraic numbers are more familiar. However, it is difficult to prove that a particular real number that we suspect of being transcendental actually are. That particular real numbers that we suspect actually are. So the book says Euler first thought of this idea of algebraic versus transcendental in the 1700s. It took about 100 years, into the 1800s, till the number e was proven to be transcendental by Hermite in 1873, and pi, probably should have put the symbol pi there, was proved to be transcendental by Lindemann in 1882. So, getting back to this extension, Q adjoin pi, pi is not algebraic, it's transcendental. And that means, ultimately, that this is not an algebraic extension of Q, it's transcendental extension. And it also means that if you think of this as being sets of rational functions in pi, where the top and the bottom are polynomials in pi, it cannot be simplified to something simpler. It's not as easy, I might say. What does this mean, almost all? I don't want to get into that. Well, maybe I'll mention it on Friday. Most real numbers are transcendental, but it's hard to prove particular examples actually are. Those are difficult proofs. The fact that pi is transcendental has historical importance as well. It's related to something called the quadrature of the circle. Anybody ever heard of that? Quadrature of a circle. You'll probably learn about that in Foundations of Math if you haven't taken that yet. Historically, 2,000-year-old problem to try to square a circle. That sounds weird, square a circle. They essentially proving pi is transcendental proved you can't square a circle, which sounds really weird, but that's the way people phrase it sometimes. Here are some foundational theorems in chapter 21. If A is transcendental, this is just emphasizing what I just emphasized. If A is transcendental over F, then F of A, the extension of A, the minimal extension of A in E containing A, is isomorphic to the field of rational functions in X. And it can't be simplified further. If A is algebraic over F, then this is in fact isomorphic to this factor ring where P of X is a polynomial minimum degree that has A as a 0 and P of X is irreducible over F. This should seem not too surprising, perhaps. We've talked about these kinds of factor rings before. They are fields when P of X is irreducible over F. And it turns out F of A is isomorphic to that. Anybody see where I put my clicker? Where is it? A is called a minimal polynomial if it's also mnemonic. There is a unique mnemonic such irreducible P of X. Okay, let's end class on this slide here. Just sit and listen. E is an extension field of F. We say E has degree n over F and write this notation, which looks kind of similar to index notation with groups, except we put a little extra, it's not just lines there, it's square brackets. If E has dimension n as a vector space over F, if this thing is finite, we call it a finite extension, otherwise we say it's an infinite extension. Theorem, if you've got a finite extension, it must also be an algebraic extension. And moreover, if you've got what's called a tower of fields, E is an extension of F and K is an extension of E, then the dimensions multiply. If this dimension is M and this dimension is N, as vector spaces over the field below, then the dimension of this over this is M times N. Real quick summary of some pretty in-depth things. But continue working hard. See you on Friday.